Hi everyone. In today's class, we can see a topic named as structural level modeling in Verilog. So in the previous classes, we have already seen three different types of modeling labeled as first one is a gate level modeling, followed by a data flow modeling, and we have also seen what you mean by the term behavioral level modeling. And the fourth classification of modeling in the Verilog is named as structural level modeling. Structural level. From this term, we can understand that the structural level represents the physical connections of the components. It represents the physical connections of the various components. It can be a combinational network or it can be also a sequential network. And this structural level modeling also represents the hierarchy of interconnected submodules. And most of us get confused with structural level modeling and gate level modeling. Both the methods are not the same. There exists a difference between a structural level whereas the gate level modeling. So I will indicate what are the key difference between structural level modeling and a gate level modeling. If it is a case of a structural level modeling, when you are indicating in terms of an abstraction level, structural level modeling has a higher abstraction level, whereas a gate level modeling has a lower abstraction level. The meaning is, in the case of a structural level modeling, the components that are going to be processed in the structural level modeling are going to be the various modules, or this also represents the various blocks that are involved for constructing the resultant circuit. Whereas why the gate level modeling is said as a lower abstraction level is because the gate level modeling will be built in with the help of gate primitives. The gate primitives, in the sense it represents the various logic gates that are involved. It can be an AND gate, OR gate, a NOT gate, or an XOR gate, or an XNOR gate, whatever might be. So this is what you have to understand whenever you are constructing a coding related with a structural level or a gate level. Since we are processing or calling more number of blocks or modules, structural level modeling has a higher abstraction level when compared to gate level modeling. And in this case of use cases, this represents a top-down approach. This represents a top-down design. Whereas when you consider the case of gate level modeling represents a detailed logic design of the circuit that is involved. Since we are representing whatever the gates that are being involved, this is named as a detailed logic design, whereas a structural level modeling uses the cases with a top-down design. And some of the examples for a structural level modeling will be instance calling. instance calling the submodules. Whereas if I consider the case of a gate level modeling, gate level modeling is basically representing the various gates that is manually, right? So to summarize it, we can say that structural level modeling has an higher abstraction level when compared to a gate level modeling. Here, top-down designs will be processed in the case of a structural level modeling, and structural level modeling will be done by instanting or calling the submodules into the main program. This is how we need to construct a structural level modeling. I will give you an example with the structural level modeling by considering a basic circuit of ripple carry adder. So if you consider the case of a ripple carry adder, you consider the case that we are going to write a Verilog coding for a 4-bit ripple carry adder. Let me write the short form as RCA. Let me consider that we are going to construct a coding for a 4-bit ripple carry adder circuit. If you recall the concepts of a ripple carry adder, the basic element that will be used for constructing a ripple carry adder is going to be a full adder circuit, right? So this will be the basic element. So what you are going to do is, since it represents a 4-bit ripple carry adder, let me take 4 different full adder circuits, and after taking these 4 different full adder circuits, I will integrate all the full adder circuits. After integrating the full adder circuit, it results in a ripple carry adder. This is the ideology what we are going to do for constructing a ripple carry adder. So you know that a full adder circuit comprises of 3 different input signals that are taken as A, B and a carry in, and it has 2 different output. One output is going to be the sum and the second output is going to be the carry. So now what we are going to do it is, we are going to take 4 different full adders in this manner and we are going to construct a ripple carry adder. So since I am taking 4 different full adders, let me use the square box for representing each and every full adder. So let me take 4 different full adders in this manner. And what I am going to do it is, since the full adder has 3 different inputs, let me connect the 3 different inputs in this manner. And since this represents the LSB, I am going to take this full adder inputs as A1, B1, and let me take one of the input as carry in. And 2 different outputs are going to be produced. One output is sum, and the second output, what I am going to do it is, I am taking the second output and I am integrating this carry output with the second full adder. So the first block represents the full adder 1, which has 3 different inputs taken as A1, B1 and Cin. 2 different outputs are taken as S1 and C0. Whereas if I am constructing for the rest of the full adders, let me consider the second full adder as FA2, having the inputs as A2, B2, and the other input is the output that is obtained from the previous full adder taken as C0. And the 2 different outputs are represented as, for sum, let me take it as S2, and for carry, I will consider it as C1. And this carry needs to be connected with the next full adder, FA3. And this FA3 along with the carry input has 2 different input taken as A3, B3, and I will consider the sum as S3. And this is further given, the carry output of FA3 is given to FA4, and this FA4 has two different inputs taken as A4, B4, and let me consider the output as S4 and carry out. This completes the diagram of a 4-bit ripple carry adder circuit. So what we have done it is, we have taken a full adder circuit, and the basic ideology for constructing a ripple carry adder is, you take the carry output of one full adder and make it as a carry input for the next full adder. This is the ideology that we are going to do for constructing a 4-bit ripple carry adder. Now, if I want to write a Verilog code using a structural level modeling, if you recall the concept of structural level modeling, what I told is, we are going to take a lower level design like a full adder circuit, and we are going to call it as a function calling, make it as an instance, and we are going to write a program for this full adder. So before writing a program for 4-bit triple carry adder, you just write a Verilog code for a full adder. This Verilog code can be written using any one of the modeling. It can be a gate level modeling, or a data flow modeling, or a behavior level modeling. For an instant of time, I'm going to write this Verilog code for the full adder by using a data flow modeling. If we are using a data flow modeling, the main thing what you have to remember is, whatever the output expressions that are available, the output expression needs to be represented using a keyword that is taken as assign. That is what you have to remember. So how you need to write the code structure is, if you consider the circuit of a full adder, the full adder has three different input signals taken as A, B and C in. Two outputs can be taken as sum and C out, where the expression for the sum can be written as A XOR B XOR Cn, and the carry output can be represented as AB into BCn plus Cna. This is how we need to write the expressions for sum and carry for this full adder. Now, when I write a Verilog code with respect to data flow modeling, you start with a preprocessor directive module followed by some module name. So what module name I am going to keep it for this particular case is, the module name I am going to take for this full adder is, let me represent it as full adder instance, and we need to open a bracket, mention the input signals as well as the output signals that are available for the full adder, and below this you write whatever the input and output statements available by using a keyword input and output. So now I have written what are the input signals that are going to be taken into account, and what are the output signals that are going to be taken into account using a separate keyword. Followed by this, since it is a data flow modeling, the output expression needs to be represented using a keyword assign. Now you write this keyword assign, and you write the resultant sum as well as carry expression. So the sum expression is taken as A XOR B XOR Cn, and the carry expression assign C out is written like A logical AND with B followed by R, B logical AND with Cn followed by R, a Cn logical AND with A. And below this you use a keyword end module, and you can terminate this particular program. So I have written the code using a data flow modeling followed by a keyword assign, and I have expressed the two different outputs sum and carry and terminated the program of full adder. Now when you check this full adder program in using a model sim software, I will just open the model sim software and I will check whether my program is validated or not. So when I open this model sim software, I have created this full adder instance program by using a data flow modeling where the inputs are taken as A, B, C in, outputs are considered as sum and carry out, and the inputs and outputs have been declared separately. By using an assign keyword, I have defined the output function and terminated the program by using end module statement. Just I will check for any compilation, any errors that are occurred during compilation. So you could see that the written program is right and it doesn't have any compilation error. So I will just run this program and I will check whether the functionality is satisfied or not. Just I will call that program. So the program name is FA instance. It is available in the work directory. I'll choose this FA instance window, and in the object screen I will select all the input and an output signal. Just right click on this and click on add wave. So you can see that a waveform window has been opened. Now let me apply some inputs for this A, B and C in, and I will check whether it is satisfied or not. So when I apply the inputs like this A, B and C in this manner, I have applied three different inputs, and when I click run option, you can see that the value of A is taken as 0, B is 1, C in as equal to 0. So if I check like this, so given value of A is equal to 0, B is also equal to 0, C in is equal to 0. Now if I compute for sum is A XOR B XOR Cn. It results in 0 XOR with 0 XOR with 0. So it will be 0. Similarly, if you take other input as A as 0, B as 1 and Cn as equal to 0, the sum will be 0 XOR with 1 XOR with 0. Now what is 0 XOR with 1? It results in 1. 1 XOR with 0 results in 1. So the resultant sum expression will be equal to 1. And when you are looking into carry out, it is AB plus BC in plus C in A. AB results in 0 because it is 0 and 1. Similarly, B and C in also results in 0. C in and A it also results in 0. So the resultant carry out is going to be 0. When I check with the results obtained in model sim, you could see that the sum output is taken as 1, carry output is taken as 0, which means this satisfies my functionality of a full adder circuit. Now what we can do it is, you take this full adder circuit as a function calling, right? You take this as a function calling using a keyword instance, and you are going to write a program for a structural level modeling. So how I am going to write a program it is, so if you consider a structural level modeling, what we are going to do it is, so what we have done it is, we have considered 4 different full adders and we have cascaded all the 4 full adders, right? So let me start with a preprocessor directive module followed by the module name. Let me take that my module name is considered as ripple carry adder. Followed by this, I am going to declare the input signals as A, B, C in, output signals as C out, right? And when you look back into the circuit that what I drawn previously, you can see that the inputs A, B are taken in the order of 4 bits, right? Here you can see that it is A1, B1, A2, B2, A3, B3, A4, B4, which means what does this represents is the value of A is taken in 4 bits and the value of B is also taken in 4 bits. Similarly, when you look into the sum expression, it is S1, S2, S3, S4. So you can see that the sum is also taken in 4 bits. Whereas, if you consider the carry in, the carry input is a single bit, right? And similarly, you can see that a carry output is also a single bit. Why I am saying it as a single bit is, the reason is because we are having only one carry input and one carry output. Then what about these C2, C1, C0? These three terms will be considered as an wire component. Why it is taken as a wire component is, the reason is, if you consider C0, for this case of full adder 1, it acts as an output and full adder 2, it acts as an input. Similarly, C1 also has the same manner. In both the cases, it acts as an input and output. If you recall the concept, whatever the input and output signals that are being taken as a common one will be declared using a net data type that is taken as a wire component. So you have to consider this as an wire component, and if I am writing a program using this ripple carry adder, now what I need to do it is, I need to declare the input signal of A and B in terms of vectors, right? And you can see that since you have used small letter a and b for representing, we will stick on the same term. So the input AB has been declared in vector, whereas input Cin has been declared in scalar. So these two terms are considered as an vectors, and these two terms are considered as a scalar. What is the difference between vectors and a scalar? Vector represents, it has multiple bits, whereas scalar has only one single bit representation. That is the difference between these two terms. Similarly, when you consider an output signal, the output signal sum should be declared in vector, and the output carry should be declared in scalar. And if you recall the concept, what does this term 3 is to 0 represents? This 0 is used for representing the LSB bit, and this 3 represents the representation for MSB bit. And below this, you use a wire component for representing the variable C0, C1, C2 separately. Now what you are going to do it is, you have already written a program for full adder by using a data flow modeling, and what is the name that is given for this full adder is FA instance. Now what you are going to do it is, you are going for a function calling, and you are going to call this program FA instance. So when I call this program in my module of a structural modeling, you can write it as FA instance followed by the full adder that you are going to process in this ripple carry adder. So when you look back into this diagram, the first full adder is given as FA1, where the inputs are taken as A1, B1 and carry in. Output is considered as S1 and C0. So I am going to write it in this expression. So I am calling the first full adder as FA1 followed by, since the vectors A and B since they are taken as an vectors, A and B should be represented in vector format, whereas carry in is a scalar one, so it is simply represented as Cn, and sum represents a vector format, so it is taken as S of 0 followed by C naught. This is how I am going to call that full adder for my discussion. So this represents the full adder circuit. In this full adder, I have called like this. Similarly, if you are calling for the second full adder, you use the same keyword FA instance followed by FA2 and the inputs that is applied for the second full adder. So in this case, you can see that I have represented C naught in place of Cn. The reason is the output of the first full adder is taken and given as an input for the second full adder. Since it is given like this, it is taken as S C naught followed by S1 followed by the next carry output of that corresponding full adder. So FA2 has a carry output taken as C1. So I am representing it as C1. Now what you could note it is the output that was available in the first full adder was being brought as input for the second full adder. Similarly, when you write for the third line, it is FA instance followed by FA3, A of 2, B of 2. Now what you need to do? You take this Cn, bring it here. So it will be C1, S of 2 followed by the output of that corresponding full adder block. Now the last case is FA instance followed by FA4. It is A of 3, B of 3. Now you take this carry output, propagate here, it is C2, S of 3, and the last output is C out. This is how you need to declare the structural level modeling. After you call all the full adders, just terminate it with an end module statement. This will be the key structure that is involved in structural level modeling. Since you have used this instance keyword as FA instance, it is a higher level design. So make sure that you don't misinterpret the two different modeling, that is a gate level modeling with a structural level modeling. In the case of a gate level modeling, the same structure might be represented using a primitive gates like AND or not, whatever might be. Now, in this case of a structural level modeling, what we have done it is, we have used that full adder design module and call that full adder, and we have created the Verilog code using a structural level modeling. That is the difference between these two key terms. Now, if I use this concept in model sim and if I simulate it for a 4-bit ripple carry adder, so here you can see that the input signals A and B have been declared in vector. Input carry in has been declared in scalar. Sum output has been declared in vector. Carry output is also declared in scalar. And we have used three different wire statements taken as C0, C1, C2. And I have called that full adder program. So here it was mentioned as FA instance. I am calling this full adder program here and I have declared the complete program. Now when I compile this, I will choose this option compile and compile selected. You can see that this ripple carry adder created using a structural level modeling is free with compilation error. Now when I simulate this ripple carry adder, just I will click on this work directory, search for the module name that I have created now. So it is mentioned as ripple carry adder. Let me choose that module name as ripple carry adder. Click the option as OK. And in this object window, now you can see that the variable inputs A, B and C in has been mentioned here. Now when I click this option as an add wave, here you can see that since A and B have been declared in the vector format, when you click this plus sign, you can see that 4 bits have been allotted for the input variable A, 4 bits have been allotted for the input variable B, whereas single input has been taken for carry input. Now when I assign the value for A, let me consider the value of A as some 1010, right? So what I have taken it is, I have taken the value of A as 1010. What does this 10 represents? This represents the first block A1 followed by A2 followed by A3 followed by A4. So 4 bits have been taken into account, right? So in our Verilog code, what we have done it is, this was taken as 0, this was 1, 2 and 3. Similarly, if I am taking for B input, it should be B of 3 followed by B of 2 followed by B of 1 followed by B of 0. Let me consider the input signal like this 0 1 0 1, and I will take the carry input value as some 0. Now if I do an addition, it results in 1 1 1 1, and you can see that there won't be any carry output that is produced, and this represents S of 0, this represents S1, S2 and S3. So this should be your expected output. Now when I provide this value for B, let me take this value of B as 0 1 0 1, and I will click OK. And similarly, let me consider the value of carry in as equal to 0. When I run this program, you can see that the output has been generated at the first case, right? Now, in this case, why it is showing these kind of errors? Because correspondingly, this ripple carry output should be altered. So I am altering this ripple carry output in this manner. Once again, I will say this program, do the compilation and run this program once again. When I click this work directory, and if I choose the option as ripple carry adder and click OK, in this object window, let me select all the input and the output variables once again, and I will append the same values in the waveform window. So what I have done it is, the value of A was assigned as 1010. The value of B is assigned as 0101, and the value of carry in is taken as equal to 0. Now if I run, you can see that the values of sum are taken as 1111, and the resultant carry is generated as 0. This is what we have done in this manipulation. This manipulation has been satisfied in this model sim, right? This is how we need to write the structural level modeling. The basic idea is, you are going for a function calling. You can call any one of the program in your main module, simulate the program, verify the functionality. This is the key idea in the structural level modeling. I hope you all have understand this structural level modeling. So thank you all for the session. Thank you.